Dear students, in video 3, we have finished up to Gibbs free energy. Nernst has given some more equation also, and today we will put focus on that. As we know, as per the Gibbs free energy from the thermodynamics, it is also related with the equilibrium. When cell does its work by its own, it means work is done and the Gibbs free energy has been reduced. Where we have calculated the Gibbs free energy by minus NFE cell and standard Gibbs free energy by minus NFE degree cell. Today we will see Nernst equation as per the relation of thermodynamics and equilibrium. As per the thermodynamics, when work is done by the system, energy is used up and it gets reduced. So as per the equilibrium, when we say that in a system or in a cell, when the work is done, and when we are talking about the cell, the potential is developed. We know now from our previous videos, the potential develops because of the separation of the charge, or we can say because of the developing charge. As the charge develops, as per the thermodynamics, Gibbs energy also changes. If Gibbs energy changes, then EMF, E cell will also change, and when the E cell changes, it will also in the relation of the equilibrium of the cells which are connected together. So, Nernst thought in the relation of thermodynamics and in the relation of the equilibrium, and from that the equation taken in the combination of equilibrium and thermodynamics, which you have already learned in 11th standard, please pay attention here. Gibbs free energy is equal to standard Gibbs energy plus RT ln Q. Now here R, you know what is delta G, what is standard G, but R, as per your 11th standard knowledge, R is gas constant 8.314 joule per mole Kelvin. T is the standard temperature 298 Kelvin. And ln stands for natural logarithm. Those who are from the maths group, they have this idea, but those who are from the biology group, you please pay attention. ln stands for the natural logarithm, and if we will put the value of natural logarithm into our exponential log, then it is equal to log to the base e, which is equal to the numerical value 2.303 log to the base 10. Why this we need? Because we have the tabular form of log to the base 10. And so whatever the value we have for the log, we will have to convert that value to the base 10. So we are in need to know about natural logarithm to the base e, which is again converted by multiplying 2.303 to the log base 10. And now please pay attention. This equation delta G equals delta standard G plus RT ln Q. From the video 3, you can put the value of delta G and delta standard G. Delta G is minus NFE cell. Delta standard G is minus NFE standard cell plus RT ln Q. Now here, we want to calculate cell potential. So, if we will divide this whole equation by minus NF, then what we will get? Dividing all this term, 1, 2 and 3. Dividing by minus NF, we will get E cell is equal to E standard cell plus RT and minus NF ln Q. Making them into the standard form, please pay attention, plus, minus. It is again a rule that denominator will never stand with the negative. So multiplying this negative to the numerator, we will get E cell is equal to E standard cell minus plus minus minus 0.059 upon n into log q base to 10. Now pay attention here. Here it is RT upon minus NF. Making the denominator standardized, we have considered multiplying negative sign to the numerator and we got here negative. But how 0.059? Remember, wherever the temperature is standard 298 Kelvin and multiplying the gas constant 8.314 with the log to the base 10 numerical value 2.303, and as in the video 3 I have told about Faraday's value 96500 coulomb. Multiplying all these value, putting into this equation R into T into numerical log value divided by Faraday's constant, we will get this standard value 0.059. And so, whenever the temperature is given T is equal to 298 Kelvin, we are always taking this equation to calculate the E cell. E cell is equal to E degree cell minus 0.059 upon n log of Q to the base 10. Log of Q, you must know, as I have written, in the relation of thermodynamics and equilibrium, Q stands for the equilibrium reaction coefficient. Thus, E cell equals E degree cell minus 0.059 upon n log Q to the base 10 is developed as Nernst equation for the non-standard condition and to calculate non-standard reduction potential E cell. On the basis of this Nernst equation, the others Nernst equation for the half cell, full cell as well as concentration cell are developed, which we will see now. Now, let us see Nernst equation for half cell in relation of standard hydrogen electrode. When it is said in the relation of standard hydrogen electrode, it means one of the half cell is standard hydrogen electrode, and we know standard hydrogen electrode, its volt is 0.00 volt. So now here half cell, equation for half cell. So we will consider the half cell in the relation of G. Let us consider one of the half cell in the reduction, that is M plus N slash N. M plus N aqueous, it means it is in the solution acquiring the electrons and electrons, it grabs the metal as an electron which is solid in form, S. Now for this half cell, looking to the formation representation, we will come to know that it shows the reduction, and let us write down the equation of it, that is half reduction reaction. M plus N gives, by taking an electron, gives metal M at temperature 298 Kelvin. Now applying our Nernst equation, E cell is equal to E standard cell minus 0.059 upon N to the log Q base 10. Here you see temperature is 298 Kelvin. So without any other calculation, we can go for 0.059 upon N. As I told, when the standard condition is there, then by putting the value of standard, gas constant, temperature as well as by putting the Faraday's value and numerical value of the log, we will get the standard value 0.059. So as soon as you see the temperature 298 Kelvin, don't go for a complete formula RT, Ln, NF. Just put 0.059 upon N log Q to the base 10. So here, to find out cell potential, see here not degree is not written, it means non-standard. So looking to the half cell, we are going to find the cell potential for Mn plus slash M is equal to standard cell of this half cell. So it will be standard value for Mn plus slash M. This we will get from the tabular form of reduction potential, that is electrochemical series tabular form, minus 0.059 upon N log M by Mn plus. Now pay attention. And here N stands for number of electrons. We will have to see the reaction. How many number of electrons are gained or are donated? Here we can see number of electron gains N. So it remains N. Right? And after gaining the number of electrons, when we get the metal, so looking to this equation, now as per equilibrium, what is this Q? I have written here M by Mn plus. But what is this M by Mn plus? Please pay attention. Here Q as equilibrium is reaction coefficient. You have learned in 11th standard equilibrium chapter, and in that Q stands for reaction coefficient. What is reaction coefficient? Q is equal to reaction coefficient. It is the value of ratio of concentration of product by concentration of reactant. Concentration of product by concentration of reactant. Now look again to this reaction. This is our reactant, left hand side. This is our product, right hand side. Reactant, product. Putting this value of reactant and product in our this formula of reaction coefficient Q, concentration of product upon concentration of reactant, we are getting value M because concentration of product, and we are getting M plus N, concentration of reactant. But now, please pay attention here. Cell potential is equal to standard cell potential minus 0.059 upon N log 1 by M plus N raised to 1. Now from where this 1 and M plus N raised to 1 has existed? So once again, pay attention here. Product here is equal to M. M is considered as the metal, and metal is attained at equilibrium. So its activity is considered unity as per the equilibrium, because metal is attained after the accepting of all the electrons, and it has attained its metallic property. So M is having activity 1, and here you see M plus N, that is concentration of reactant. On the reactant side you see M plus N with stoichiometric coefficient. You please pay attention here, raised to 1 I have written. What is Q? Reaction coefficient. Pay attention here in the reaction. What is the coefficient of this reactant? 1. What is the coefficient of this product? 1. As per the equilibrium, it is reaction coefficient. So for the concentration, we are supposed to write down its coefficient as the power. And so here, from the reactant sides, the reactant is M plus N. Its coefficient is 1. which is to be taken as the power which will develop the stoichiometric of the coefficient, and it is taken over here, and as it is metal, its activity is unity 1, and on the reactant it is in the charge form, so m plus n with with power 1. And thus, for the half cell in the relation of standard hydrogen electron, now the Nernst equation is developed as E cell equals E standard cell minus 0.059 upon n log 1 by n plus n to the coefficient power to the base 10. So whenever the calculation of cell potential for the half cell is to be considered, the Nernst equation is given this form. Let me explain you one example. So you will easily understand the value of all this in the Nernst equation. Example 1. Here, standard value for the cell copper is given 0.34 volt. Standard E degree is given. It means this value is already given in the ECS table. At 298 Kelvin and Cu plus 2 written in the square bracket. If you remember equilibrium chapter of 11th standard, square bracket shows the concentration. So Cu plus 2 square bracket shows the concentration 0.01 molar. Then find E cell. Here degree is not written. It means we are finding cell potential which is non-standard condition, NSRP. Now if I will see this representation of the half cell, Cu plus 2 slash Cu, you must know charge is given and taking a position of the metal. So reduction reaction is taking place here. Please pay attention. Cu plus 2 gives us the idea plus 2 electron is gained and it is now copper metal attained. So putting the value of this half reaction into our equation, E cell is equal to E standard cell. Please pay attention, this is E standard cell. E standard cell 0.34 minus 0.059 upon, see here, N. Now look to this reaction. How many transfer of electron takes place? 2. So N stands here, 2 electron log to the base 10. Now please pay attention. Log Q. Q means M by M plus N. So here, what is this M? Looking to this product copper metal, as I have made metal, its activity is 1 as equilibrium. So 1, and here you can see there is no coefficient, so raised to power 1. And you see in the denominator, it is M plus N. M plus N, that means on the reactant side. So reactant side you can see here it is Cu plus 2. So taking the concentration of Cu plus 2, it's given to us 0.01. So 0.01. Looking to the reaction, there is no coefficient of the Cu plus 2. So here the power is only 1. Now please pay attention this. Log of 1 to the power 1 divide by 0.01 to the power 1 to the base 10. How we are going to get the value of the log? So 1 by 0.01. It means it will be log 100 to the base 10. Now log 100. It means 10 square. And you know as per the log formula, log of 10 to the base 10, it is equal to 1, and so it will be 2. That means log of 100 to the base 10 is value 2. Putting this 2 here. Whole this value is now 2. So this 2 and this 2 if we will cancel. Putting the value this 2 for whole this term 2 and 2. 2 in the numerator, 2 in the denominator will be cancelled. So we will get 0.34 minus 0.059 which is equal to 0.281 volt. So the cell potential for this given half cell is 0.281 volt. Thank you.